It's just some function. Got it? All right. And what we're going to do is illustrate the fact that the gradients are actually associated with the variables in TensorFlow, right? Whereas in calculus, like when you do the analytical thing, it's associated with the function itself, okay? And that may not be intuitive to you if you've seen this before, but just keep that in mind, right? The variables are what holds, so they're just evaluated to the derivative. So it's almost like if you have these values and you plug them into this function, you get some value. And then if you have the derivative of this function, you get another value, the result of it. You see that, like the plus, minus, and so on. Make sense? Okay, so that's the idea. All right, so then for this function, we can work it out. Work it out as, by plugging in those values, f would be 3, 5 square, right? Plus 2 to the 5 times 3, correct? And that should be 3 times 25 plus 30, basically, right? And that should give us 105. So this is the analytical solution to this, right? We just plugged in the values in the function. We'll do this in code in a second. Okay, so it gives us 105. Then over here now, the calculus thing, what that means is that it takes these derivatives of that function, right? With solving it through the analytical solution should be, I'll write the function again, f equal 3w1 square plus 2w1 times w2, right? So then we're going to take, so now you take a derivative. So I'm going to say a, which is going to be the derivative of that function in terms of w1. You see that because you do it in terms of that parameter that you're looking at, right? Why? Because you're optimizing for that parameter. Do you guys see that? So remember that the value that you get for this parameter is the one that determines plus, minus, 0. That's it. Don't worry about anything else. You just want that mechanism, okay? So in this case, this is the partial derivative of f with regard to w1, right? So that should be then, let's see. So you guys are experts. So this is going to be, sorry. So this should be 6w1, correct? For the first part, w1. And then plus, what is the next part? 2w2? 2w2, right? Because it's the derivative in terms of w1. You see that? Don't worry if you don't know this, you know, that it's not important. What's important is this is the loss function j, and then you take the derivative of it. And what happens is you had this function, you had this function, and now you have that function. Do you see that? That's what TensorFlow is doing. That's it. And then for those values that we had before, where are they? W1 equal 5, W2 equal 3. What do they represent? They're the tensors, right? The values that you need to solve for. Okay, so now this becomes, the solution is 6w1 plus 2w2. Okay, we also then have to, for the other parameter, w2. You see that? See how, imagine if you have 52 billion parameters, you have to do all of this. You see that? You see that? You can't do this from scratch. You need these. This is where TensorFlow does all of this for you. Okay, so let's do the next one. So it's going to be derivative of the same f, the original one, but in terms of w2. All right, so you guys then can tell me here, in terms of w2, what is the value? The first one becomes what? 0. 0, right? Yes? Right? And 0. And then the next one becomes what? 2w1 from this one, right? Because you're deriving in terms of w2. Yeah, so it should be 2w1. So I'll get rid of this 0 here. Oops. And again, how do you know this? Calculus has these rules, right? And you have these solvers. but what's important is you derive in terms of one weight and the other weight, right? And this is how you figure out then that plus, minus, or zero that's going to update the weights. Does that make sense? That's exactly what's happening behind the scenes. All right. So now that we have the two functions, so TensorFlow has solved this for you, right? And now what you do is you just plug in those values, right? So in theory, this should be what? This should be 5, correct? Plus 2, 3. So that's going to be 36. Do you see that? So the value itself is what you get because you had, and you have the values, the tensors, right? And then you have an original function, the loss function. And then as you're doing stochastic gradient descent, you're calculating these derivatives. So you go from the original function to these new functions, okay? And then now in these new functions, you evaluate the original values, W1 and W2. So we did 5 and 3 here. That gave us 36 for W1, right? For W1. So this would be for W1, right? Because that's the, well, yeah, in terms of W1, I should say. And then for the next one is going to be what? 2 times W1, which is 5. So that's going to be 10. Those are the two values that we get. And that's what TensorFlow is going to give us. Got it? Any questions? So let's go over the code. So we've done this in the analytical solution. Now let's take a look at this. We're going to write we're just going to play with the gradient, the gradients calculation in TensorFlow, one of the ones that are available. Okay. So we're going to write this code. I've already installed some of these libraries, so you guys will probably need to install them. You can just copy them. So I'll just copy the code from the GitHub. So I'm going to go ahead here. Okay. I'm already in the environment. So I'm going to start the Jupyter Notebook. Now, this is not just this, this is not stochastic gradient descent. This is just what, stochastic gradient descent relies on this to be able to update the weights. Okay. So we're going to start a new Python script here, Python 3. It's not C. Oh, there it is. Okay. So we're going to call this gradient calculation. And again, this is just to illustrate what's going on behind the scenes. Okay. So I have code here. Gradients, so you can just get it from there. The code is available to you. So basically, I'm going to copy some of the libraries. And you'll see some of the mechanisms that are available in TensorFlow. So here I'm using NumPy, TensorFlow, and Matplotlib just to plot things a little bit, right? So run that, load the libraries. Like I said, this will break for you probably because I already installed that MPL toolkits. So it should just be pip install MPL toolkits, I would think. Let me know if that doesn't work. And also pip install matplotlib. And the other two you should have. Remember, this is in the GitHub, so you can just copy it from there. Any questions while this is going on? So while it's doing that, remember this was the function basically that I just wrote by hand. It's literally the exact same function. So I just made it into like an actual function in Python. Notice it's the W1 squared times 3 plus 2 times W1 times W2. That's it, right? So that's the function. All right, it's taking a while. So if you I'm gonna go to the whiteboard while it's still loading. So you can see here, we started with, we need these two values, 5 and 3, and we have this function here, right? That's the one that I just added the code for. So then the first thing we might want to do is just plug in W1 and W2, and we should get 105. Okay, we should get 105. Let's try to do that. All right, it finished. Good. So no errors. All right, so now I'm going to hit run. I've loaded the function. Okay, now we can take a look at the, let's see, I'll create some ranges later, but let's just make the call. All right, so if you notice, that's the function, and I provide the two values 5 and 3, right? Oops. 5 and 3. Okay, so this should give us 105 if I run it. And there it is. We get 105. That's it. All right, now just like you can do the analytical solution by hand, as I showed you, pretty much you can do it via TensorFlow. The only thing is, if you've ever done a lot of this analytical solution by hand, then you expect somehow to get another function, and that doesn't happen in TensorFlow. TensorFlow does things behind the scenes. What it gives you is the values, right? That's it. And so that's sometimes I have found that over the years, it's not intuitive how that works, but that's how it works. Okay, because that's really all it cares about. So it's not a module for calculating derivatives, it's a module for optimization of neural networks. Okay, we're also going to need some ranges for the plotting, so I might as well copy them before I forget. So I'll copy this. Okay, so I created some ranges from 0 to 10 for the X and the X called X1 and X2, and they're for the W1 and the W2. All right, so just so that we can plot things, have some values. So you can see here, generated that data. Okay. Then we can go to here. You can plot this. All right, this is just, I'm just going to copy this code just to plot given that function, right? Given that function, what that function kind of looks like. Okay. This is the function, not the derivative of the function, but the function itself, okay? You can see that, so that's kind of what it looks like. So the analogy is that you're thinking of, if you were thinking of the quadratic, right? So if we go back to the whiteboard over here, I think we started, right? Remember this, guys? Right? So the quadratic just looked like this bowl shape, yeah? That x2, and then we take the derivative of it and find out for the values where they fall in the tangent of it, right? So what we're doing here is we're just plotting that function kind of in the same sense, okay? Luke is going to give us a solution of when you take the derivative of it, and he's going to earn some points for it. All right, so yeah, so that's kind of the idea, okay? So let's go back here to the code so that underscores that. Right, so now we have this function, and now we're getting close to the point where we want to take, just like I did the analytical solution, we want to see this feature of TensorFlow that does this as well. And this is called calculating the gradient. I think it's really important that you guys are aware of what this is, so that you don't get confused when people start talking about the gradients and whatever. You should have a sense of what they're doing and the importance of it. Oh, there's another plot actually called the contour plot, which is actually better for visualizing, because here you can't really tell where 105 falls, right? It's a little bit difficult to know, where's 105. So there's you can also plot what is called a contour plot, which is this one, which is also provided for you guys. So I'm going to hit run on that one. And so seeing 105 for 5 and 3 should be a little bit easier, right? So 5, 3, kind of here, right? In this area, and this area, according to the color grade, yeah, is 105. Do you guys see that? So this is like a light blue type of a thing. So light blue. It's just another way of visualizing things. But it's because 105 is that 3 and 5. All right. So I'm gonna hit save. Okay, then okay, so I plotted that. Okay, now we are actually going to proceed to calculate the gradients, which is just fancy terms for saying we're doing some kind of a derivative, right? And I kind of just want to demystify that. So here I'm going to add just a little title, markdown, hit run. All right, so now calculating the gradients. Now, as I said, it's not so intuitive in the beginning how TensorFlow has implemented this, because really what you do is you create the variables, right? So if you notice, now I'm going to create that W1 and that W2. So I'm going to grab the other one. Okay. And if you notice, they are now tensors, right? They are TensorFlow or TF.variables, tensors of values 5 and 3. Does that make sense, guys? So you can imagine there's a computational graph that holds these two tensors, right? And they're tied to an equation. That equation you calculate the derivative of, and then these values run through that one to get the results that we should have gotten with the analytical solution. So I'm going to hit run here, right? And I've created basically the variables are initialized. All right, then I'm going to go over here. And now comes this thing that TensorFlow has invented called the gradient tape, which I literally think is like they thought of a tape and now they're sticking things on that tape. You guys see what I'm saying? Like it's literally called that. As you can see, the gradient tape. So with tf.gradient tape as tape, and basically what that means is that they're sticking things to that whenever they want to do this kind of thing. All right, so they're sticking here what? Notice the function, right? So you have z, and c now is starting to represent a graph, a computational graph. Got it? And what is a computational graph? It's basically what? Two tensors, which are W1 and W2. Do you see that? In some relationship. And the relationship is what? The equation itself, right? F. And that is defined, if you remember, by this one. All right. So all of this becomes like a computational graph in TensorFlow. Okay. So if we go back to the whiteboard, this is actually how everything was explained back in the day. So like when you start reading through that book, the course notes, chapters 1 through 4, you'll see that a lot of the discussion is the computational graph, which is still there, but it's just not mentioned so much anymore. So if I have my notes here, somewhere. So it's like you've created these tensors, W1 equal 5, that's a tensor, and W2 2 equal 3, that's a tensor. But now TensorFlow, right? So you need to create a computational graph. So there's an operation 2, right? Square, basically, of 2. Let's say, actually, that should be. The operation is squared. Okay. And then you have another operation, which is multiplication, right? Times 3. You see that? So you start to lay out this computational graph in memory. That's what TensorFlow is doing. And that's why it's called TensorFlow, right? So all of this is happening. Here you have W1 also with a operation, or you can say the result of this, actually. The result of this, right, gets connected to the rest. And so you start creating this entire computational graph that captures the function, okay? So that's how it works. Any questions on this? Does this make sense, guys? Yeah, so it's a graph that represents either the tensors or the operations on the tensors. That's it, okay? And then that is stored in memory somewhere. And then when it comes time to calculate the gradients, it just does it. Right? For that graph, it calculates the gradients. It just does it on its own. But this is how it's set up. Any questions on this idea? Clear? All right, great. All right, so now let's finish up that script. So I'm going to go back to the code over here. Okay. All right, so we've got the gradient tape. So if you notice, we've said TF gradient tape as tape. We tied and actually, I'm going to do this in the next line. So we've tied now the 2 tensors to the function, and we can reference everything by Z. That's the great thing about it. C becomes like the thing that we can grab, and it refers to the entire computational graph. Okay, so I'm going to hit run on that one. And then now I can add this one here. So if we look back, if you notice what happens here, now you just say tape. Tape is the thing that holds everything together in this sense, and you just tell it gradient, dot gradient. At that moment, you're telling it to take the derivative of C in terms of W1 and W2. Got it? So now you have the results in gradients themselves, right? So that should give us a couple, should give us a couple of values. Let's do run. Now I'm going to just do gradient. Gradient, hit run, run. And it gave me an error. Oh, yeah. Okay. There we go. Did it work? When we did the analytical solution, right? It should have given us 36 and 10. Right? So if I go back to the whiteboard, we did it somewhere here. So if you notice 36 and 10. You guys see that? Yeah. And now if we go to here, 36 and 10. There we go. That's it. But so that's it. I mean, that's literally all I wanted to show you. You don't even use gradient tape to do the actual gradients. You just say step or, whatever, right? Atom optimizer step. But they created this gradient tape so that you can somehow maybe sometimes play with the graph itself and look at it. At the end of the day, what my point is, if you've done this a lot analytically, you probably wanted to see the function, but that's not how it works. Instead, everything is tensors and the value of the tensors after the gradient has been calculated. Questions? And now these are the values that, fall into this idea. If I go over here, right back to the whiteboard to conclude, so now they represent this, right? So the indication of this tangent on the loss function, and now you can update the weights because you know if it's a positive, negative, or 0. Got it? And I'll do one last example that concludes the code actually. So let me just look at it. I think, yeah, that was it, right? So we did it. You can just copy it from the GitHub and run it on your own, play with it. But I want to do another example. So a neural net, usually the intuition, right, that we look at in a neural net is that, we've said something like, it looks like this, right? It has multiple local minima, global minima. A lot of work goes into this idea. A lot of people try to smooth these. They have techniques where, like, they may actually make them smoother, and that intuitively makes it better, right? But what we're doing is, if you're here, let's say, we do one more. Yeah, like that. And you're kind of like there, right? So you want to figure out, okay, I need to go in that direction. That's what that accomplishes. And hopefully you read the paper, right? Remember, I provided a 3-page paper for stochastic gradient descent. That's in the GitHub. Don't forget to read that one. That's from the authors themselves. So you can also, but this is the mechanism that does it. So this was not possible. This theory has been around. It was invented in 86, right? But it wasn't until we had enough computing power that a lot of these things could be done. All right. And so this PyTorch, TensorFlow, and all those tools that do deep learning basically do this. Okay, do these derivatives as we saw, but for billions of parameters. Efficient. Any questions, guys? Does this make sense? All right, so that's kind of it as far as that idea.